Welcome to Wireless LAN Weekly, a podcast focused on the wireless networking professional. We aim to educate, inform, entertain, and inspire. Get ready to listen and enjoy. Now to our host of the show, Keith Parsons.
Hello there, listeners. Glad you're joining us back for episode 17 of Wireless LAN Weekly. Today is another special episode. This one is focused entirely on technology. We've brought back Dave Hutchieson, and Dave, with his nice Scottish accent and technical expertise, is going to share with us the details of how secure sockets layers works. Fairly detailed subject. You will definitely need to look at the show notes and follow along with the graphics and the links that have been provided. We definitely want to thank Dave for all his effort and time in researching the subject. It's something we all really need to know how it works. It affects us in our daily lives, but we normally just ignore and just look at SSL as something that happens. And it does just happen, but it's kind of nice every now and then to really know how something works. So thanks again to Dave for doing this here. Big warning goes out to everyone. This is going to get fairly detailed. You might want to listen to this a couple of times. Maybe go back and listen to it, let it soak in slowly. It's kind of easy to let the mind wander while Dave's talking. I mean, he's got a nice voice, easy to understand, but the subject is fairly detailed, and we'll be getting into quite a bit of that detail during our session today. So let's go ahead and get started with the podcast. Enjoy Secure Sockets Layers.
Today's wireless networking definition from the CWNP Dictionary of Wireless Terms and Acronyms.
Noise floor. This is the level of constant residual noise in a system. It's often used as a reference point in the signal-to-noise ratio.
Rant, pet peeve, what really bugs you? 60 seconds of complaining starts now.
Hi, this is Jeff Keenan. I just wanted to talk today about something that bugs me. When customers call in asking for wireless routers, we mostly sell access points. That's what you use in a hotel or enterprise to extend the wireless range. But a lot of times the beginners, all they know is the word access point is the same as a router. So because they buy the router in the local Best Buy, and they don't sell access points there.
Things every wireless LAN professional needs to know. Gear up, buckle down, and stand by for the real techie stuff.
Hello again, this is Keith Parsons with Wireless LAN Weekly, and in today's episode, in this segment, we've brought back Dave Hutchieson. And Dave will be sharing his wealth and breadth of knowledge today, specifically on SSL, Secure Sockets Layer. And if you want to follow along with the graphics are available on the website as part of the show notes. So, Dave, take it away.
Hi, Keith. Yeah, thanks for asking me back. About the topic of today, I thought that we'd discuss secure sockets layer, because what I've found over the years of dealing with security is that if you've got a good understanding of secure sockets layer, or SSL, it forms a keystone for understanding more complex protocols that are used in security. And also it covers quite a large range of things. It covers symmetric key encryption, it covers public and private keys, it covers certificates, and it covers hashing. So that was why I wanted to cover it today. If you have a good knowledge of SSL, I think it serves very well as a foundation for future studies. So I'll get started. Secure Sockets Layer, or SSL. Part 1, Historical Background. In order to get the most from this audiocast, a basic knowledge of symmetric key encryption, public and private key mechanisms, digital certificates, and hashing functions is assumed. If this is new material to anyone, or you feel you need a review, please refer to the tutorial web link included in the show notes. A ladder diagram showing the step-by-step processes involved in SSL is also provided in the show notes. It is suggested that this diagram be referred to whilst the audiocast is in progress. Wireless security is one of the most complex topics imaginable. One of the biggest problems is the number of acronyms and abbreviations that are in use. There are a number of security mechanisms in use, such as EAP-TLS, EAP-TTLS, EAP-PEAP, EAP-FAST, etc., etc. It would be nice if there was a common route that could be studied in order to get a foundation for how some of them work. One common type is EAP-TLS. EAP-TLS has its roots in TLS, or Transport Layer Security. Transport Layer Security, in turn, has its roots in SSL, or Secure Sockets Layer. I have found that if you have a good enough how SSL works, that can provide a stepping stone to understanding many of the more complex wireless security methods, such as PAP. In this audiocast, we shall look at the Ssl protocol in detail. SSL is not only used as a basis for several wireless security protocols, but is also used in HTTPS, Hypertext Transfer Protocol Secure, which is often used for managing access points in a secure manner. There are support materials provided in the show notes section, and these have diagrams which may be viewed to accompany the audio portion. SSL is a very complex protocol, and due to time constraints, we'll not be able to discuss all the details that are involved. However, it is hoped that by the end of the audiocast, and with the support of the show notes, that you should have a good foundation for future study. In a future audiocast, we shall look at how TLS was developed from SSL and how EAP-TLS was developed from TLS. In the early 80s, companies sprouted up all over the place, trying to sell goods and services to people. There was a major problem, however, and that was the issue of security. If someone wanted to buy something, that would probably mean that they'd have to provide their credit card number over an open line. A method of hiding that number from prying eyes had to be developed. The issue of confidentiality or privacy had to be covered. There was also the problem of having confidence that the company that you're going to buy something from was actually that company and not an imposter. The issue of authentication had to be covered. It was from this background that the Secure Sockets Layer, or SSL, was developed. Part 2, Ssl Overview. SSL was designed to work on top of a secure transport layer protocol such as TCP or Transmission Control Protocol. We can get a clue about this from the use of the term sockets in the phrase SSL. The designer of SSL to accomplish three main goals. 1, to provide privacy of information. 2, to provide authentication, although as we shall see later, this is not always mutual authentication. 3, to provide a method of message integrity, which would allow us to detect if a message had been tampered with en route from the sender to the destination. The SSL protocol has 2 layers which sit on top of a reliable transport protocol. In our discussion, we shall assume that protocol is TCP. The uppermost layer comprises 3 sub-protocols. 1, the SSL Handshake Protocol. 2, the SSL Change Cipher Spec Protocol. And 3, the SSL Alert Protocol. The lowest layer comprises the Ssl Record Protocol. The Ssl Record Protocol performs a number of functions. Firstly, it takes the applicant data and divides it into a number of fragments when necessary. The fragment size should be no more than 16,384 bytes in length. The specification says that we can compress these fragments. This is rarely, if ever, carried out in practice due to compression already having occurred further up the protocol stack. A message authentication code is then added to each fragment. Each fragment is now encrypted and an SSL header is added. The secure, integrity-enabled fragments are now passed on to the transport layer. We will see later how we obtain the keys used for the actual encryption process. Part 3, SSL and Detail. We shall now look at the 3 uppermost protocols, the Change Cipher Spec Protocol, the Alert Protocol, and the Handshake Protocol. The Change Cipher Spec Protocol. The Change Cipher Spec Protocol allows us to change from one encryption state to another in an organized manner. We shall see more of this later. The Alert Protocol. The Alert Protocol allows warning messages to be passed between the 2 parties. For example, if an incorrect message authentication code is received, an Alert Protocol message would be sent from one party to the other. The Handshake Protocol. The Handshake Protocol is the meat of the entire system and is the most crucial component for TLS and EAP-TLS. Imagine that you're a police officer and your lieutenant tells you that you have to go over to the United Nations to talk to a UN security officer about a very important matter. The officer will be waiting for you at the entrance. Upon arrival, you walk up to him and say hello. He looks at you with puzzled eyes. You realize that your boss has not told you what language he speaks. You say bonjour, no response. You finally say buenos dias. His eyes light up and he says, buenos dias, como está usted? You shake hands, show each other your ID badges and start talking. In social situations, we don't usually just walk up to someone and start talking. We usually say hello and shake hands. Sometimes we need to establish a common language. So it is with SSL. Instead of just starting to communicate, hellos need to be said and handshakes need to take place. There are 4 main phases to SSL: negotiation, authentication, key exchange, and ongoing communications. Let's look at each phase now. Negotiation. During the negotiation phase, the client and server introduce each other and decide which encryption, authentication, and compression protocols will be used. Noted that even though the capability for compression exists in the SSL specification, it is rarely, if ever, used. Authentication. In the authentication phase, the server proves itself to the client via a digital certificate. The server may also ask the client to prove itself via a digital certificate. It should be noted that in the case of internet shopping, this is rarely, if ever, done. Key exchange. In the key exchange phase, a key is exchanged which will be used in creating a master key for encrypted communications. There are several methods by which this can be done, including the Diffie-Hellman method, which I shall discuss in a future audio cast. For now, we shall only discuss what is called the RSA method. Firstly, the client randomly generates a key called the pre-master secret key, or PMSK, by means of a method that will be covered when we discuss SSL in more detail a little later on. Firstly, the client encrypts the PMSK with its own private key. This allows the server, who has a copy of the client's public key, to authenticate that the PMSK did indeed come from the client. The whole assembly, that is, the PMSK encrypted with the client's private key, is now encrypted with the server's public key, which came via the server certificate and sent to the server. The server decrypts the package with its own private key. This now leaves the original PMSK, which has been encrypted with the client's private key. The server decrypts this package with the client's public key and hence authenticates the original PMSK. This original key is not the final key in the process, but is used along with some other items to create the final symmetric key, also known as the master key. From the master key, session keys can be derived. Communications. Now that both sides have symmetric or master keys, they can exchange messages in an encrypted manner. Digital signatures can also be provided to help ensure authentication and message integrity. Now we are ready to discuss the detailed step-by-step operation of the SSL Handshake Protocol. Step 1, client hello. This message begins the entire process. The client hello message is sent from the client to the server. There are 4 main things that are included in the message. 1, a random number called clienthello.random. This random number will be used to create a key later on in the process. The random number consists of a 32-bit timestamp along with 28 bytes created by a random number generator. 2, a list of Cipher Suites and compression methods that the client supports. 3, the highest version of SSL that the client supports. 4, a session identifier that indicates whether the client wishes to establish a new connection on the current session or establish a new connection on a new session. The session identifier is useful for going back to previous web pages, for example. So what is a Cipher Suite? A Cipher Suite consists of a listing of encryption methods, certificates, and integrity checking methods. The client cannot just simply say, I'm going to use this value of encryption, this certificate, and this integrity checking method. It has to check with the server to see if the server is actually capable of using any of the methods.
Interesting facts, little-known tidbits, things you might not have known, short little bits to set your mind a-reeling.
Hey, this is Derek Sisterhen. Did you know that 55% of people say they can't survive for 3 months without a paycheck? Kind of begs the question, what are we doing with all this money we're making when we do receive a paycheck? Probably should be putting a little bit of it aside in case we ever have an emergency.
Elevator speech. Our guests have just 2 minutes to tell us all about their product or service offering. Ready, set, go.
Hi, this is John Freeman with Xeris. We're the creators, manufacturers, and designers of the Xeris Wi-Fi array, providing 2 times the coverage, 4 times the capacity of standard access points, and user densities up to 16 times what a standard access point can deliver to you in legacy environments.
Things every wireless LAN professional needs to know. Gear up, buckle down, and stand by for the real techie stuff.
Step 2, server hello. The server hello message is sent from the server to the client. There are 4 main things that the message contains. 1, a random number called server hello.random. This number will also be used to create a key later on in the process. 2, the Cipher Suite that the server wishes to use, chosen from the list supplied by the client. 3, the lowest common value of the version given by the client and the highest that the server supports. For example, if the client suggested 2.0 and the server supports up to 3.0, the 2.0 version of SSL would be used. 4, a session ID number. This number uniquely identifies the current session and helps with security. The Cipher Suite is made up of 2 main parts. A, the key exchange method. That is how the keys will be exchanged. For example, this could be the Rsc Method, Diffie-Hellman method, etc. B, the Cipher spec itself, which is fields which tell us the algorithm being used, for example, RC4, DES, etc. The MAC algorithm, for example, MD5 or SHA1. The type, for example, stream cipher or block cipher. And finally, the hash size, for example, up to 16 bytes for MD5 and up to 20 bytes for SHA1. Up to this point, unique random numbers have been exchanged, an encryption method has been agreed to, and a unique session identifying number called the session ID has been generated. Step 3, server certificate. At this point, the server sends the client its digital certificate. This point is very important, as not only will the client use a key provided in the certificate to encrypt messages back to the server, but the certificate provides proof that the server is what it says it is and not an imposter. The client will have previously been provided with a public key from the certification authority. This authority, for example, could be a reputable organization such as VeriSign. At this stage, we have to carefully distinguish between the 2 public keys mentioned. The first public key has been provided by the certificate authority. That is an independent certifier who basically says, if you can validate the certificate that you've just received from your server using that public key that I provided to you, you can be certain that the server is who he says he is. Once the certificate has been verified, the client extracts the server's public key from the certificate. This key is very important. Any messages encrypted with this key can only be decrypted by the server using its own private key. Step 4, server key exchange. A server key exchange message may be sent in this step. Only some systems require this. In our example of using regular RSA, we do not require this step. Step 5, client certificate request. In this step, the server may request a certificate from the client via certificate request message. This message has 2 areas of interest. Firstly, a certificate type parameter. The certificate type would cover RSA or Diffie-Hellman, for example. The second item concerns certificate authorities. This would give a list of the distinguished names of certificate authorities whom the server deems to be, quote, reliable, unquote. Step 6, server hello done. At this point, the server hello done message is sent from the server to the client. This is the end of the first phase of the protocol exchange. To summarize, hello messages have been sent from the client server. An encryption method and other security parameters have been agreed to. The client has its own random number and that of the server. The server has its own random number and that of the client. A certificate has been sent from the server to the client and possibly one from the client to the server. The public key of the server has been extracted from the server certificate, ready for use in the second phase. A point to note, there are no formal first and second phases in the TLS specification. I have simply broken up the process into two parts in order to, hopefully, make the process easier to understand. In a future audiocast, I'll be covering another EAP method which does have two officially defined phases. Step 7, client certificate. In this step, if the server has requested a certificate, then the client will send one. In the classic case of SSL being used in HTTPS for internet transactions with, say, an online clothing company, the customer client would not normally have to provide any formal identification with the exception of, say, a credit card number. This is obviously somewhat of a problem, as it means that fraud could and in fact does occur. Step 8, client key exchange. In common with many other security protocols, a true master secret key is not sent between the two parties. Instead, a key called the pre-master secret is created and sent from the client to the server. This pre-master secret will then be used at both ends of the link to create a true master secret key. A random number is generated at the client, and this number is referred to as the pre-master secret key, or PMSK. Firstly, the client encrypts the PMSK with its own private key. This private key is known only to the client. This allows the server, who has a copy of the client's public key, to authenticate that the PMSK did indeed come from the client. The whole assembly, that is, the PMSK encrypted with the client's private key, is now encrypted with the server's public key, which came via the server certificate, and is sent to the server via client key exchange message. The server decrypts the package with its own private key. The server's private key should be known only to the server. This now leaves the original PMSK, which has been encrypted with the client's private key. The server decrypts this package with the client's public key and hence authenticates the original PMSK. At this stage, both sides have the pre-master secret key. In the next part, the actual or master secret key will be calculated at both ends of the link. The master secret is calculated using a complex hash function involving the pre-master secret, the client hello.random, and the server hello.random variables or nonces that were described earlier. The master key is 48 bytes in length. From the master key, a number of other keys are derived. These keys are now used for encrypting data sent by the server, for MAC operations performed by the server, for encrypting data sent by the client, operations performed by the client. Initialization vector values are produced for the situation in which block ciphers in CBC mode are used. Step 9, client certificate verification. A certificate verify message is sent if the client previously provided a certificate to the server. This message is only used with certificates that have signing capabilities. Step 10, change cipher spec. It should be noted that the change cipher spec protocol is a separate protocol from the Handshake Protocol. It has been included here due to its critical function within the Handshake Protocol itself. SSL keeps a record of two states called the current state and the pending state. We can think of these two states as conditions that are happening now and conditions that will happen later. When SSL is first initialized, both states are 0. Once the master key is established, that key is used for a pending state. Both sides end up with a pending encryption process waiting in the wings, so to speak. The pending cipher spec is copied into the current cipher spec. We just need some form of agreement between both ends as to when to begin implementing the encryption. This occurs in the next step. Step 11, finished. The finished message is used to tell the other end that the key exchange and authentication procedures were successful. This message is encrypted with one of the newly produced keys and authenticated as well. Once the server receives the encrypted finished message from the client, it is able to send its own change cipher spec and finished messages in steps 12 and 13 of the process. Finally, we're able to encrypt any data that needs to be sent from either party. That was quite a lot of material, but the core of the whole process, as for many other security protocols, consists of negotiation, authentication, key exchange, and ongoing communications. In the show notes section, I've included an interesting trace of a client-to-server communication process. I hope that this audiocast was useful, and thank you for listening.
Well, Dave, thanks for your expertise there. It was good to, well, a little tedious, I admit.
Yeah.
It definitely helps to have the show notes pictures to follow along, because I was kind of following along as you went through and did that.
Yes. I know it's long, but I find that SSL is really critical to good understand a lot of these protocols, and there's a lot of information in there. I've had to deal with a lot of security problems before, which were not solved because people did not have a good understanding of public key encryption certificates, etc. And I thought this would just summarize a lot of issues there.
Well, it was very helpful because from a troubleshooting standpoint, there's a lot, every one of those little steps along the way is a potential flaw.
Exactly.
And so you need to know how it's supposed to work so you can come back and find out where it's failing.
Yeah, sure.
Well, thanks again for your time today. I appreciate your effort in preparing this, and we'll get it out on the podcast.
Yes, you're welcome, Keith.
Thank you. Well, that was sure a long and detailed explanation of how SSL works. Again, you might want to go back and listen to this a couple of times, let it kind of sink in, follow along with the graphics. Next week, we'll come back with a little lighter tone, some of the easier things to talk about with respect to wireless LANs. We're glad you joined us again for another week of Wireless LAN Weekly, and hope to see you next week. Thank you.
Wireless LAN Weekly, a podcast focused on the needs of wireless LAN professionals. We look forward to your feedback. Please leave your comments at the bottom of the show notes, or email feedback on the show can be sent to feedback@wirelesslanprofessionals.com. If you'd like to leave a voicemail feedback, just call 24/7 and leave a message at 1-801-481-9018. Until next time, this has been another production of wirelesslanprofessionals.com, a place to educate, inform, entertain, and inspire.